go.
Here we go.
Hopefully the computer's working. I don't know. Hello, everyone. Welcome back. I'm Steve. Good afternoon.
And I'm Scott.
So I don't know if you can believe this article from UC scientists. I don't know. It seems kind of fishy. We'll give a go at it. Tell us what you think. Scientists at UC Berkeley had developed a new platform called Oz that can simultaneously control up to 1,000 photoreceptors in the eye, offering new insights into the mechanisms of human vision and the causes of vision loss. In Frank Baum's original novel, The Wonderful Wizard of Oz, the Emerald City is described as such a brilliant shade of green that visitors must wear green-tinted glasses to protect their eyes from the brightness and glory of the city. The glasses are one of the wizard's many deceits. Viewed through green-tinted lenses, the city would, of course, appear even greener.
Now, using a new technique called Oz, scientists at the University of California, Berkeley have found a way to manipulate the human eye into perceiving a brand new color, a blue-green hue of unparalleled saturation that the research team has named OLO, which blue-green used to be called hazel, right? Didn't we used to call that?
No, it's spelled OLO. What does that look like to you? That looks like a phallic symbol. OLO.
Is that a like text talk or something? Or
maybe text talk. Yeah, weird. UC Berkeley.
Yeah.
Okay.
Saturated natural color is just pale by comparison, said Rorda, a professor of optometry and vision science at UC Berkeley's Herbert Wertheim School of Optometry and Vision Science, and one of the creators of Oz.
Okay, so Oz works by using tiny doses of laser light to individually control up to 1,000 photoreceptors in the eye at one time. Don't know if I want 1,000 lasers going into my eye. Okay, I've had LASIK.
Yeah, I'm not doing that.
And they kind of cut the retina, and then they pulled the retina up, and then they, or they cut the, what's that, corona? Not corona.
What
cortex? No.
What if they have an oops while they're doing that?
Yeah, that's the thing, man.
Taking
that's the thing, man. I was able to show not only right.
Yeah. Now we're talking totally.
This is from the researchers. Okay. Yeah. The platform could also be used to answer basic questions about human sight, vision loss, and life.
Okay.
The big question, why?
The Oz technique is described in a new study recently published in the journal Science Advances on April 18th, 2025.
So it was published.
Yep. So just not quite a month ago. The work was funded in part by Federal National Institutes of Health photoreceptor cone cells in the retina. Each type of different wavelengths of light. S cones detect shorter, bluer wavelengths, and L cones detect longer, reddish wavelengths.
Wonder how they find out. Wow. How do they do that?
I don't know.
It could be making it up. I don't know. However, due to an evolutionary quirk, the light wavelengths that activate the M and L cones are almost entirely overlapping. This means that 85% of the light that activates M cones also activates L cones. Quote, there's no wavelength in the world that can stimulate only the M cone. It's stuff, and Professor a professor of UC Berkeley, quote,
who had created a technology that used tiny microdoses of laser light to target and activate individual photoreceptors. Rohr calls the technology a microscope for looking at the retina, and it is already being used by ophthalmologists to study eye disease. But for a human to actually perceive a whole new color, Ing and Rohr would need to find a new way to activate not just one cone cell, but thousands of them. So
yeah, Fong first started working on the Oz project in 2018. As an graduate engineering student, has created much of the complex software needed to translate images and colors into thousands of tiny laser pulses directed at the human retina. For Oz to work, first you need a map of the unique arrangement of the S, M, and L cone cells on an individual's retina. To get these maps, the researchers collaborated with Ramkumar Sabasan and Vimal Prabhu Pandyan at the University of Washington, who have developed an optical system that can image the human retina and identify each cone cell.
With an individual's cone map in hand, the Oz system can be reprogrammed to rapidly scan a laser beam over a small patch of the retina, delivering tiny pulses of energy when the beam reaches a cone that it wants to activate, and otherwise staying off. The laser beam is just one color, the same hue as a green laser pointer, but by activating a combination of S, M, and L cone cells, it can trick the eye into seeing images in full Technicolor. Or by primarily activating the M cone cells, Oz can show people the color O.
Oh, Roy Div. See, so this is kind of slanted. The researchers did it. See, I don't know, man. The researchers participated in the were the test subjects. I don't know.
Yeah.
I don't know. Described it as blue green or peacock green. It reported that it was much more color. What are the dots? They said they saw dots and babies. Doyle also tried jittering the Oz laser. Oh my gosh, man. This is on your eye, and they tried jittering it,
creating an oops.
Directing it ever so slightly off target so the light pulses hit random cones rather than only M cones. The participants immediately stopped solo and starting the race.
It's a figment of the eye's imagination, right? Because if you're moving it, you should still be able to see it. Although it's kind of like a rainbow, right? When the sun starts moving around and the water stops, or it becomes more. There's more water, more rain. The colors change, right? Isn't that how that works?
Yeah, so light is going through the
refraction,
through the raindrop. Yeah.
Yeah. So Oz isn't just useful for projecting tiny movies into the eye. The research team is already finding ways to use the technique to study eye disease and vision loss. They are also exploring whether Oz could help people with color blindness to see all the colors of the rainbow, or if the technique could be used to allow humans to see in tetrachromatic color, as if they had 4 sets of cone cells.
4 sets.
Now we're up to 4 sets.
4.
Yeah. It may also help answer more fundamental questions about how the brain makes sense of complex world around us.
Yeah. So
again, we were just talking before we went on. So I'm colorblind, or I've got a color deficiency, and I can see colors. I just can't differentiate. But I would not. It's not that big a deal to me. I'm not going to freak out and go get this procedure done.
You're not going to run over there?
No.
I mean, UC Berkeley's just 6 hours away.
I'm not going anywhere near Berkeley, but even if it was in Apple Valley or Victorville, I wouldn't do it. So it's just
well.
not that big a deal to me. You know, I mean, my world has been my world for 90 years, so it's, you know, it is what it is.
You look good for 90.
Yeah,
you look really good.
I pride myself on being in pretty good shape for 90.
All right, folks, thanks for joining us. Catch us in the morning. We have another very interesting and stimulating show. Click the like button. We'll see you tomorrow morning.
Take care, everyone. Thanks for watching.